Welcome to section 9.2. We'll be talking about geometric sequence and series. Our goal is to determine when a geometric series converges and compute its sum when it does. All right, let's look at what a sequence that's geometric is. So 9.2.1 geometric sequence. Here's an example, 9.2.1. What comes next? Find the next two terms in the following sequence. So it starts with 2, then minus 6, then 18, minus 54, and you need to come up with the next two. This is something that appears in IQ tests. I don't know if you've ever taken one. All right, so I don't know if you've noticed the pattern, but here the term gets multiplied by minus 3. And then if I multiply minus 6 by minus 3, I'll get 18. And if I multiply that by minus 3, I will get 54. So I'm assuming that the pattern follows this continues like that. So here I'm going to assume that the next term is gotten by multiplying minus 54 by 3, so I get a positive number, 162. All right, and keeps going, so I'll get a negative number, 6, 18, minus 486. And the sequence continues that way. All right, so that's what a geometric sequence is. So a sequence is geometric if there is a real number r, so that for any an plus 1, you can get from an by multiplying by r. So here, this would be geometric with r equals minus 3. The r is called the ratio of the sequence. It's called the ratio because for a sequence to be geometric, if you look at what r is, you're going to put an to the side, an plus 1 over an, that's the ratio. So the an plus 1 over an should all have the same value, and hence they should not depend on n. All right, so the first thing I want to do is I want to just check whether a sequence is geometric, and if it is, find its ratio. So example 9.2.2, determine whether the following sequences are geometric. If so, find their ratios. And we'll worry about sums and everything like that afterwards. All right, so if I take 2 over 3 to the n, I want to look at the ratio of an plus 1 over an, and I want to see whether I can simplify it to get just a number and not anything that depends on n. So here, you could write it in terms of AK if that's easier for you. If you're fine with just n, that's fine. I'm going to take k equals n plus 1, and that's going to be the top. So I'm going to get 2 over 3 to the n plus 1. I like to write it like this, and you'll see why in a second. I'm going to put a big line, and then I'm going to put 2 to 3 to the n underneath. I like it like this because it makes it clear that I'm taking a fraction of these two ratios. Often if you have a fraction over a fraction over a fraction, the notation get confused, and I know some of you made that mistake on the test. All right, so now I need to simplify this. I'm going to leave the numerator, and then if I have a fraction in the denominator, I'm going to flip it. So here I'm going to get 3 to the n over 2. The 2's here get canceled. I get 3's cancel as well. If you want to remember what the rule is, you take the power of the top minus the power of the denominator, and so I get 3 to the minus 1. And so the ratio is 1/3. So as long as what you get doesn't depend on n, as long as what you get doesn't depend on n, it's going to be a geometric sequence. And I have the ratio of 1/3. All right, let's try a second one. Let's do the same thing exactly. I'm going to look at the ratio of an plus 1 to an, and I'm going to try to see if I can't simplify it. So here in this case, ak is 1 over k squared. And so an plus 1 over an, I'm going to get 1. I replace k by n plus 1. And then underneath, I replace k by n. All right, so I get n over n squared plus 2n. Oops, sorry about that. 2n plus 1, sorry, n squared. All right, you can't split this because the sum is in the denominator. Um, at this point, I mean, you could bring it down if you wanted to and just divide each term by n squared, I guess. But it still depends on n, so no need to do that. Let's not worry about trying to simplify it. It looks like it depends on n. So it looks like n will not go away. Let's see if that's true. First term is 1 over 1 squared. Second term is 1/4. So here, if it's a geometric sequence, then I would need to multiply by 1/4. So if I multiply by 1/4, I would need this to be 1 over 16. The next term, if I plug in 3, I get 1 over 9. So this sequence is not geometric. All right, so I want to look at geometric sequences a bit more because we'll be looking at geometric series soon, and we'll be using that type of series when we do applications to annuity at the end of this chapter. All right, so assume that we have a geometric sequence AN with ratio R. I want to look at what the terms look like. So let's consider the terms of this sequence. So A1, I'm just going to call it A. A is the first term. You could call it A1. A2, well, every time I go down one step, I multiply by R. So A2 will be A times R, A1 times R, which is A times R. A3, well, I multiply A2 by R, and so I'm going to get an extra r, so r squared. So every time you get an extra r, a r cubed. And so for n equals 4, you get 3. For 3, you get 2. So for n, you will get a times, and then you get 1 less than your order in the list. All right, proposition 9.12.1. Any geometric sequence can be written as a r n minus 1, where a is a1, the first term, and r is the ratio. All right, so let's practice that, and then we'll be ready to attack series. Rewrite the sequence as a r to the n minus 1. All right, so we said this is from n equals 1 to infinity. Sorry, forgot to write it. So a is the first term, so it's n equals 1. I get 3 to the 0 over 2, 4 to the 2. So I get 1 to the 16 times 2 to the 32. All right, so A is 1 over 32. R is a bit more complicated. You have to take ratios, but we know how to do this. We've done it a few times trying to prove that things are trying to prove that sequences are geometric. And so here again, just in case you need it, let me write the terms in terms of k. N plus 1, that's going to be 3. I put n plus 1 where k is, minus 1. Then 2, 4, 2, n plus 1. Don't forget the parentheses here. It matters for the 2 at least. And then over 3n minus 1, 2 times 4 to the 2n. All right, this is what I get. I'm going to flip the denominator again. So 3 to the n. 2, 4 to the 2n plus 2. And then I'll have 2 times 4 to the 2n and 3 to the n minus 1. You can use the rule we used last time of taking the exponent of the top minus the 1 from the bottom, or if you're good at this, you can just realize that you have one extra 3 compared to here, so you'll be left with a 3. the 2's actually cancel, and you have 2 extra 4's compared to this, and so you'll get 4 squared. Again, if you need to take the exponent of the top minus the one of the bottom, that's fine. You'll get the same thing. You'll get 3 on 16. All right, so that means 3 to the n minus 1 over 2, 4, 2 to the n equals a r to the n minus 1. I feel like this looks a bit insane. This is nice and clean, so we'll use this notation often, especially when trying to prove things about geometric series, even if we don't use it in examples, because in examples we can just find R and use it. We don't have to rewrite the whole sequence, but once we start proving things, then this is going to be helpful.